Second generation, 1954 to 1962. Second-generation computers replaced vacuum tubes with transistors, making computers smaller, faster, cheaper, and more reliable. They used magnetic cores for memory and allowed for high-level programming languages such as Fortran and COBOL. The second generation of computing, spanning from 1954 to 1962, marked a period of profound evolution and refinement in the field of computer design. A new era dawned, featuring crucial advancements at all levels of the computing system, from circuitry to programming languages. In this period, electronic switches transitioned from vacuum tubes to more reliable discrete diode and transistor technology with a much improved switching time of about 0.3 microseconds. TRADIC, built at Bell Laboratories in 1954, and TX0, constructed at MIT Lincoln Laboratory, were among the first computers to incorporate this cutting-edge technology. A pivotal innovation was the introduction of magnetic cores for memory storage. This represented a significant departure from the previous method of mercury delay lines, where data was stored as an acoustic wave that moved sequentially through the medium. The magnetic cores allowed for random access, meaning data could be accessed irrespective of its physical location in memory, a game-changer in terms of efficiency and speed. This generation also saw substantial advancements in computer architecture, such as index registers and floating-point units. Index registers streamlined loop control, simplifying the manipulation of arrays. The floating-point units represented a leap forward for calculations involving real numbers. Instead of executing floating-point operations via software routines, as was the practice in early computers, second-generation machines performed these tasks in hardware, speeding up computational processes. Software technology took a giant leap forward, too, with the birth of several high-level programming languages. Fortran, 1956, ALGOL, 1958, and COBOL, 1959, made their debut, vastly simplifying programming tasks and expanding the potential of computational applications. Key commercial machines of this era, like the IBM 704 and 7094, added I/O processors to improve data flow between I/O devices and main memory, optimizing performance and efficiency. Notably, the second generation also bore witness to the creation of the first two supercomputers designed specifically for numeric processing in scientific applications. The term supercomputer denotes a machine that outshines its contemporaries by an order of magnitude in power and performance. Two machines from this era, the Livermore Atomic Research Computer, LARC, and the IBM 7030, also known as Stretch, rightly earned this title. They pioneered overlapping memory operations with processor operations and introduced a primitive form of parallel processing, cornerstones of the supercomputers we see today. The second generation brought about the transition from vacuum tubes to transistor technology, significantly improving the speed of electronic switches. Memory technology evolved from mercury delay lines to magnetic cores, allowing random access to data. Index registers and floating-point units were introduced, advancing computer architecture. High-level programming languages like Fortran, ALGOL, and COBOL emerged, simplifying programming and broadening computational capabilities. The first two supercomputers, the LARC and IBM 7030, were built during this generation, setting new benchmarks in computational power.